Today, we are diving deep into one of the biggest battles happening in medicine right now. We're talking about a fight against one of the toughest diseases out there. And the weapons being used? Well, they're straight out of the future. Artificial intelligence, super advanced imaging, and a level of data-driven understanding of cancer that's just incredible.
I want you to take a good look at this number. Just 11%. Let that sink in for a second.
Because that number, that's the 5-year relative survival rate for someone diagnosed with pancreatic cancer. It's one of the lowest for any cancer, a statistic that has just stubbornly refused to budge, even with decades of medical progress.
And that leads us to the big question, the one we're going to tackle here. Why is this disease so incredibly deadly? And, maybe more importantly, what can our most advanced technology actually do about it?
You know, pancreatic cancer is a true paradox. We live in this age of mind-blowing medical breakthroughs, but this one disease remains a massive, staggering challenge.
So here's the thing. The problem isn't just that it's an aggressive cancer, it's that it's basically a ghost. The early symptoms are either super vague, easy to dismiss, or there just aren't any at all. And that means a shocking 85% of people are only diagnosed after the cancer has already spread, when surgery, our best shot, is off the table. This is exactly why it's the third leading cause of cancer deaths in the US and is on track to be number 2 by 2030. The real challenge here is detection. It's all about finding it early.
So, how do you fight a ghost? Well, you invent a new way to see it. And that's precisely what AI is doing for medical imaging. It's giving doctors this powerful, brand new set of eyes.
Think about this. Right now, even the most experienced radiologists using traditional CT scans miss almost 40% of early-stage pancreatic tumors. I mean, they're hunting for these tiny, subtle signs that are just incredibly hard for the human eye to catch. But for an AI that's been trained on millions of images, those same subtle signs can be as clear as day.
And this isn't just a theory. We've got the data. Look at the Panorama study. They put an AI system head-to-head with a team of 68 really experienced radiologists. The AI hit a diagnostic accuracy score of 0.92, which was statistically better than the human experts, who scored 0.88. Now, this isn't about replacing doctors, not at all. It's about giving them a tool, an assistant, that just sees more.
And this is where it gets really amazing. Look at its ability to spot the tiny, early-stage tumors, the ones smaller than 20 millimeters that give patients the best chance for a cure. The AI sensitivity was almost 99%. That's a full 10 points higher than the human readers. It's finding the cancer exactly when it's most treatable. That's a game changer.
Okay, so we can see the tumor better. That's huge. But just seeing it isn't enough. To really fight it, we've got to understand it. We need to decode its fundamental biological blueprint.
And that's where this field called multi-omics comes in. The best way to think about it is like a detective building a case. Genomics is like looking at the DNA evidence. It checks for genetic mutations, basically typos in the cancer cell's instruction manual. Then, proteomics comes in and analyzes the proteins. Think of these as the fingerprints left at the scene. It shows us what those faulty instructions are actually making the cell do. When you combine all these layers of data, you build a complete, high-definition profile of that specific tumor.
And what this deep analysis shows us is pretty profound. It turns out pancreatic cancer isn't just one disease. It's at least 4 different diseases, and each one has its own metabolic personality. Some are kind of quiet or quiescent, saving energy. Others are like little engines supercharged on specific fuels like pyruvate or glucose. And this is way more than just an academic detail. It's a battle plan. Once you know a tumor subtype, you can predict how it's going to behave and, crucially, find its unique weaknesses. It's like finding out one enemy tank runs on diesel and the other runs on electricity. You can pick the perfect weapon to shut each one down.
So, we can see the tumor, we can understand its biology. Now what? How do we get all of this complex information to a doctor in a way that's actually useful in the real world? This is where large language models, LLMs, are stepping in as the ultimate clinical assistant. See, the problem with our modern electronic health records is that the most critical information, all the details about a patient's history, their symptoms, their past treatments, it isn't in some neat, organized database. It's buried in paragraphs of text and notes that doctors write for other doctors. A traditional computer program can't make sense of that, but LLMs, they're built to read and understand human language. And this has a massive, direct impact on how patients get treated. Let's take surgical planning. Before AI, surgeons had to spend so much time manually digging through pages and pages of reports. Now, with an LLM, all of that text gets instantly summarized into one standardized, easy-to-read report. One system, for example, cut the review time for surgeons by 58%. That frees them up to focus on the actual surgical strategy, not paperwork.
And it goes way beyond just making things more efficient. LLMs are letting us be proactive. There's a model called PANDA that chewed through hundreds of millions of patient records and literally learned how to predict who's at a high risk for pancreatic cancer up to 5 years before they'd ever be diagnosed. And for people who already have cancer, AI is matching them to the perfect clinical trials, a super complicated, slow process that now happens almost instantly. It makes sure nobody misses a shot at a breakthrough treatment.
All right, so when you start weaving all of these incredible threads together, the AI-powered imaging, the deep multi-omic understanding, and the LLM clinical support, you really start to get a picture of a completely new era of cancer treatment.
We're moving on from the old way of doing things. You know, those rigid clinical trials where everyone gets the same treatment and you might have to wait years for an answer. The future is adaptive. It's all about flexible trials that can literally change course based on how a patient-specific tumor is responding in real time. It means we learn faster and we can get the right drugs to the right people way sooner.
And you can really see the whole evolution right here. We started with this blunt instrument, one-size-fits-all chemotherapy. Today, we have targeted therapies that go after specific genetic weak spots, like the KRAS mutation. But where we're headed, where we are now, is the era of these adaptive platform trials like Precision Promise. These can test multiple drugs at once and dynamically move patients to the treatment that's most likely to work for their unique tumor subtype. It's truly personalized medicine in action.
It's just this incredible convergence of biology and technology all coming together, and it leaves us with a really powerful and hopeful question. As our tech gets exponentially better at seeing the unseen, decoding complexity, and personalizing this fight, are we finally on the verge of turning one of our deadliest diseases into a manageable and maybe one day a treatable condition? The fight is far from over, but for the first time, it feels like the tools might just be powerful enough.